m equals 0 here, you will get e to the 1 here. It will be just a constant. So is it physically possible or not for the function to be a constant? Remember in the particle in a box problem, we had a similar situation here. Then we had argued that in the particle in a box problem, there we were using symbol n for the quantum number. This 0 was not allowed physically because the function was sine function, and sine 0 would give 0, which is in contradiction to the known fact that there is a particle, because if the function is 0 everywhere, it means probability of finding the particle is 0, so that is physically not possible. So we had eliminated 0 in the particle in a box problem. However, here, when you put 0 to m here, we do not obtain 0. We obtain just a constant. Therefore, 0 is physically possible for the m number. Next, we ask whether negative integers give different results than plus integers. For example, our function is e to the I times phi. For m equals minus 1, it is e to the minus I times phi. The answer to our previous question, whether negative integers give different results than plus integers, to decide on this, you must conclude whether this function is different from that function or are they the same functions. This is and this one. Now, by comparing these two expressions, what can you say? Are they same or different functions? Just imagine you take some numbers for phi. Select any value within the full range. What is the full range? 0 to 2 pi. Select some numbers and calculate cosine part and sine part. Are you going to obtain the same complex number or different complex number? Different. That means the functions are different. All right? So this function is a different function than that one. And therefore, they represent two different states of the particle. Every different state function means a different state. Similarly, for other integers, we obtain two different functions, whether we use positive integers or negative integers. Okay, then the full set here, all of them, are available for m. Now, we attach the m subscript to the function as a subscript. So we have phi 0, phi 1, phi minus 1, etc. These are the labels for the functions. We use the m value as a label for the function and attach it to the subscript. Now, before we continue with the main problem, the rotation in 3 dimensions, but it's a rigid rotor. Let us take a simpler problem. The rigid rotor has a fixed distance during rotation to the origin, which we called R0. R0 is a given number, part of the data. Now, if this particle is further restricted such that it is confined, the rotation is confined to the plane, XY plane. This means our angle, theta angle, is pi over 2. Remember, this is the z-axis, and the theta angle is measured from the z-axis. And how much, what must be value of the angle, theta angle, so that the point is on the xy plane? It is just 90 degrees, pi over 2. So let us take this example as we have a particle connected to some point. Let us say there is a nail here, and it's just rotating on the plane. And its distance never changing. But only if we draw it here, the rotation is like this. It may rotate either that way or in the opposite way. Such a particle has how many degrees of freedom? How many variables do you need to locate it? 2 variables? Okay. Which 2? If you use Cartesian type variables, for instance, are you going to use x variable and y variable? Okay. But is x independent of y? Can you select x equals 2, y equals 5? No, because x squared plus y squared has to be equal to r0 squared. So the motion is in 2 dimensions, but there are constraints here. So reconsider your answer. How many degrees of freedom do we need here? You may start with xy, okay, xy, but there is a relation among them. X squared plus y squared must be equal to r0 squared. Therefore, you may only select one of them. If you select x, you have to calculate y. That's what's meant by independent variable. Independent variables must be independently selected. But here, can you do that? No. So how many independent variables do we have here? Only one. That one variable, selection of the variable is simpler if you use polar type variables. So if you select r variable and angle variable, polar, all right. R has a fixed value, R equals R0, so that our independent variable phi describes this problem completely. Phi is this variable. I can select any value for phi between 0 and 2 pi. For a given value of this angle, can we locate where the particle is in 2 dimensions? We can, because this R0 is fixed. Just select one value for phi, and you know where the particle is. So The rotational problem that we discuss here is called rigid rotor with 1 degree of freedom. Or I will shorten it, 1 degree of freedom rotor. The variable is phi. It means we just need one variable. This type of rotation is also called particle in a ring. Because this is a circle here, or it's a ring, and the particle is always at some point on the ring. So let us now solve the energy problem, eigenvalue, eigenfunction problem for this type of motion. Our Hamiltonian is square of L divided by 2 times moment of inertia. L square is x component square plus y component square plus z component square. But in this case, because the rotation is on the xy plane, the only non-zero component for angular momentum is the z component. X component and y components are 0. Is that clear? Only z component is non-zero. And therefore, this is equal to and the Schrödinger equation is all right. Now, as z square this expression, but we don't have to know the definition of LZ square. All we have to know is this. The Hamiltonian is a constant, which is 1 over 2i, times LZ square. All right? Now we ask, does LZ square commute with Hamiltonian? H is a constant times LZ square. Constant is 1 over 2i. LZ square itself, does it commute with C times LZ square? In our discussion about operators in the introduction, we had learned some simple cases where we immediately decide that whether operators commute. One case was an operator commutes with any power of it, or any expression which contains the powers. Expression means a constant times a certain power plus another constant times operator to some other power, the operator commutes with all of those. Here, one operator is Lz square, the other is C times Lz square, and I'm asking you, does this commute with that? Of course commutes. All right? So, H commutes with Lz square. Why is this important? Because if you have two operators, and if you know they commute, then they have the same eigenfunctions. So, eigenfunctions of H are the same as eigenfunctions of Lz square. All right? Next, we have Lz. Now we are asking, does Lz commute with this expression? An operator commutes with any power of itself or any combination of its powers. Lz commutes with C times Lz square. Does it commute with 1 times Lz square? Of course. All of these three operators commute with each other. So, H, which is C times Lz square, Lz square, and Lz are commuting operators. So what does the general principle say? All of these operators, there are how many? 3 of them. All of them have the same set of eigenfunctions. Now, do we know the eigenfunctions of Lz? Here they are. All right? Therefore, these functions must also be eigenfunctions of Lz square and also eigenfunctions of H, because H is very simply related to Lz, C times Lz square. This is a concrete example showing you how if the information about commutation of operators help you in solving the problem. The solution of this problem is very, very simple, this problem, because of this fact. Because now we have learned that psi must be this function, these functions. They satisfy same functions, or let us use this symbol. If you once again apply Lz to this function, you will just get one more factor, h bar m. So what are the eigenvalues of Lz square? Operator function, constant times function. What are the eigenvalues of Lz square? H bar square times m square. Now, same functions are also eigenfunctions of Hamiltonian. Hamiltonian is just C times Lz square. All right, h bar square, m square. So what are the allowed values for energy? Now you compare this expression with this one. Remember, phi function is psi. This psi. So here, operator, which is Hamiltonian, function times constant times same function. There, the symbol we use, this, what is this symbol? Energy symbol, isn't it? What is this E in terms of M? What is this? This is E. All right? So, E is, now let us substitute C also. What was the definition of C? 1 over 2I. We have h bar square divided by 2 times moment of inertia times m square. All right. This factor, this is a constant, this part. H bar square divided by 2I. I is a constant, H bar is a constant, and so on. Now, E has unit. What unit does it have? Say if you use SI units, joule unit. Now on the right side, does M have a unit? What was M? Integer, plus or minus integer. So the net unit of H bar square over 2 times I must be, come on, joule. All right. So let us write this once again here. H psi equals E psi. H is as Z square over 2I. Psi are the functions phi m, which is equal to 1 over square root of 2 pi times e to the I m phi. The energy values are constant. This constant, we will use this symbol, capital B. This is a standard symbol, B. Energy values are given by B times m square. And here, m is 0, plus or minus 1, plus or minus 2, and so on. The constant B, which is h bar square divided by 2I, is called the rotational constant. Later, we are going to apply more general rigid rotation to rotation of diatomic molecules, such as O2, such as H2, such as hydrogen chloride molecule. All of those, every different diatomic molecule has a different rotational constant, because the moment of inertias are different, depending on which molecule you are talking about. Because as the molecule changes, first of all, the mass will change. Also, in the application to diatomic molecules, the R0 here, this one, becomes just the bond length. And the bond length is different from one diatomic molecule to another diatomic molecule. Therefore, every different diatomic molecule has a different value for B. So it is a characteristic property for a diatomic molecule. But we will come to that later. Let us now show the energies using an energy level diagram. Here is the expression. What is the lowest possible value for this expression? Which m? These are the allowed values for m. So which one, if you select, will produce lowest value? You see that b is a positive number. This is its square, m square. It's also positive. Therefore, all energy values are positive numbers. Do you expect this fact from the beginning? Just think of it classically. This is a rotation, okay, but is there any forces which are trying to change the rotation? No, free rotation. So there is only kinetic energy, isn't it? And you know that kinetic energy always has what kind of numbers? Could it be negative number? Kinetic energy? No. Therefore, kinetic energy, all kinetic energy values must be positive numbers. These are the quantum results, but quantum results cannot change the fact that kinetic energy values would become, cannot change the fact that all kinetic energy values are positive numbers. So all these are positive. So, lowest value, what is it? M equals 0, then you get 0. Let us attach to the energies. So this is what is the next value? As m increases, energy will increase. If we put m equals 1, then the energy will be B. But we could also put minus 1. Energy has the same value. But these, if for m equals plus 1, this function, and if you put m equals minus 1, are those two functions same or different functions? Different functions, which means different states. So there is a degeneracy here. This is m equals 0. This is m equals 1. This is minus 1. Now, how many fold degenerate is this energy, B? How many states are there? 2 states. Doubly degenerate. You see that all higher m values, all higher energies are also doubly degenerate. The next energy you put 2, and then you get, because this is square, this is 4b, it is doubly degenerate. This is 2, this is minus 2. The next one, 9b, at 9b, so, how can we describe generally the energy levels? The lowest energy level is non-degenerate. There is only one state. for m equals 0. All the others are doubly degenerate. For each other energy, B, 4B, 9B, etc., there are two state functions. And notice the spacing between one level to the other one. It's very, very similar to the particle in a one-dimensional box problem. Particle in a box problem had a similar expression, F's times n squared, right? This is also the same. But notice that in the particle in a box problem, there was no level at energy 0, but here there is a physical state at m equals 0. So now let us ask whether in this motion, is there a 0-point energy? What was the definition? The difference between lowest energies. One of them, quantum result, the other is classical result. Classically, what do you expect for the lowest kinetic energy? 0. This is the quantum result. Do we have 0 as part of quantum result? You see it here. Therefore, it's the same as classical expectation for the lowest value, which means 0 minus 0 is 0. When there is something is 0, we say it doesn't exist, or no 0-point energy. What type of motion is this? Is it translational motion? This is a rotational motion. So you should say, because when you say 0-point energy, it is general. There is no rotational 0-point energy. Let us now do an example. This is exercise 2 in this chapter. And the question is, what is the ground state energy of 6 non-interacting independent electrons if it is assumed that each electron is rotating like a 1 degree of freedom rotor? Ground state energy. It means that we have 6 electrons. And these 6 electrons are not repelling each other, or they cannot, of course, attract. They have the same charges. But we are assuming they are not repelling each other. They are non-interacting, which means they are independently moving. Any one electron among 6 electrons does not know that there are 5 more electrons. Independent, non-interacting electrons means that. First, we start with the ground, lowest energy for the 6 electrons. The application here is more than one particle. Here we have 6 particles, 6 electrons. And the model is this. Whenever any model is applied to electrons, which factors do we have to take into account? Pauli exclusion principle. What does it say? In simple form, any orbital, the occupation number of any orbital cannot be more than 2. The orbital can be either unoccupied, or singly occupied, or doubly occupied. The orbitals in this problem, in this model, are just these. These are the orbitals. They are represented by these dashes on the energy level diagram. All right? So, to get the ground state for the total of 6 electrons, we select the lowest orbital, lowest energy orbital, which is this one, and we use it for how many electrons at most? For 2 electrons. One with up spin, the other with down spin. We have 4 more electrons. We have to use the next orbitals for the ground. Here is 2. There are 2 more. This represents the ground state energy of 6 independent electrons which are moving according to this model. What is the total energy? This is ground. 2 times 0 plus 4 times B, and the other orbitals are unoccupied. Therefore, the total ground state energy of 6 electrons using this model is 4 times B. You may consider this as a very naive application, but actually this model is applied to symmetrical planar conjugated hydrocarbons, such as benzene molecule. Benzene because of the resonance structures, the bond length between one carbon and another carbon is the same in benzene. So this is 1.40 angstrom. This is also so all of the carbon-carbon bond lengths are the same. Now, as chemists, how do we think about the motion of the pi electrons in benzene? As far as are they retained between carbons like the sigma electrons, or are they more free to maybe rotating around the molecule? That's the picture in our mind about pi electrons in benzene, isn't it? Now, with that picture, we think about this model. Here we have a rigid rotation around a circle, and our chemical picture for pi electrons is these pi electrons are just circulating around the molecule, in the benzene molecule. Now, all we have to do is to associate the required parameters. What is B? This is I here. But what is I? Mass times R0 square. So to do a numerical calculation, what data do I need? I need to know numerical value of this mass. But if I say I'm talking about electrons, then it is the electron mass, isn't it? This mass is mass of electron when I apply it to the benzene molecule. Another data that I need is value of R0. What is R0? Radius of the ring. Now, how do I obtain it? Just enclose the benzene. You can enclose the benzene inside a circle. Then the radius of the circle is this. But this has the same value as that one. And in fact, this is an equilateral triangle, which means this distance is the same as that distance. And this is just one length, isn't it? 1.40 angstrom. So, the idea here is similar to our application of particle in a box model to linear conjugated molecules. Remember, I had done an example for hexatriene molecule. Hexatriene, double, single, there are three double bonds, but the molecule is linear. There, we said that we can visualize the pi electrons as moving back and forth. And then we applied the particle in a box model. The idea here is very similar, but this time the molecule is not linear. It's a planar molecule, very symmetric. And then we just enclose a circle around it. So estimate the value of R0, which is just the bond length in benzene molecule, then apply it here. So, but experimentally we cannot measure absolute energies. Experimentally we can only measure the energy differences. So what does it mean? We can ask, what is the excitation energy? To excite, what is the lowest excitation energy? Which means just excite one of the electrons. This is HOMO. This is lowest unoccupied orbitals. If you excite one electron here to there, the total energy will increase by 3b. It will become 7b, but we need delta E, which is just 3b, isn't it? This is the lowest excitation energy. You may obtain it 4b minus 1b, which gives 3b, or you may calculate the total energy for the excited state, which is 4b plus 3b, and then subtract 4b, you will obtain the same number. Delta E is 3b. With this information, mass of electron, (9.1 times 10 to the minus 31 kilogram. Of course, such numbers you always look up from the constants section in textbooks, or in the examination I will give all such values. Mass of electron. R0 is 1.40 angstrom. Now, it means 140 picometers, isn't it? Pico, 10 to the minus. Nano is minus 9. Pico, next. What is it? Minus 12. Angstrom is minus 10. We calculate B using SI units. 3.117 times 10 to the minus 19 joule. In the calculation here, you need to calculate first moment of inertia, which is this number multiplied with square of this number. and you should obtain 1.8785 times 10 to the minus 50. What is the unit of moment of inertia in SI units? You see the units on the right side. What is the unit, SI unit for mass? Kilogram. What is the unit for R? Meters. It is square. So meter square. So this is then B is here given. So what must be the frequency of photon which will cause this excitation? If we call this symbol for the frequency of photon, the photon energy must be equal to delta E. In order to cause this excitation, delta E is 3 times B. H 6.626 times 10 to the minus 34 joule times second. So the frequency of light to cause this excitation is this number divided by that number. You should obtain 1.411 times 10 to the 15 hertz. Knowing this number, you may express it in terms of wavelength of the light. What is the relationship between frequency and wavelength? Frequency times wavelength is equal to C. So from that relation, using numerical value of C and this number, wavelength of light, 212 nanometers can be found. Fine. We are stopping here. On Friday, during the first hour, I am going to continue with the full two-dimensional rigid rotor. That part is not included in the exam, but so far, up to now, including 1 degree of freedom rotor, it will be included to the exam on Sunday.